This is RVAC, and in this series, I'm going to show you exactly how I made it and what it does. I've been working on this project for well over a year, and a part of that is because of how complex these type of vacuum cleaners are. In one of my previous videos, I made a simple robot vacuum cleaner, but it was not at all as capable as modern vacuum cleaners are. They're much more complex, and the most fascinating part about their functioning is how they're able to map and navigate around the house so that they do not miss a single spot while cleaning. So, to be able to do all of that, RVAC needs to be able to move, scan the environment, and process the information to generate commands. After a lot of research and planning, I came up with some rough designs and bought these NEMA 17 stepper motors to move the wheels precisely, so that I hopefully wouldn't need wheel encoders for odometry, letting the robot know roughly where it is with respect to where it started. As for the brains of RVAC, this Raspberry Pi 4 here is what runs the navigation algorithms and commands the motors of the robot. So first things first, I designed a cutout of the base in Fusion and CNC'd a 4mm MDF board. After trying some methods for mounting the motors firmly, I used some of the scrap pieces and bolts and made this mount for the stepper motors. Next, I bought this caster wheel for the front. I masked it and painted it black before mounting it onto the base with another small board of MDF and some bolts like this. As for the wheels of the motors, I couldn't find any pre-made wheels with the same shaft size as the NEMA motors. So I bought these wheels and made a tube of sorts with aluminum cans, so that the wheels could fit snugly onto the motors, which seemed to work fine, except one of the wheel's shaft was ever so slightly slanted, which caused the whole wheel to swivel a lot, so I ended up replacing that wheel by buying two more. Now to control these motors, I used these A4988 stepper motor drivers, which I stacked one on the other, and an Arduino Mega which receives instructions on how to move from the Raspberry Pi and converts them into frequency of steps for the motors to move. And as for the Raspberry Pi itself, once I got it and opened it, I stuck the heatsink before mounting it on top of the Arduino using another piece of MDF. Now to power the whole system, I got this 4400 mAh 12.6 volts lithium-ion battery pack. The reason I didn't use a power bank is that there are very few which were compact enough but had enough power for the Raspberry Pi and all the other electronics on board. So instead, I used this battery pack with a buck converter to power the Raspberry Pi. Because nothing could ever possibly go wrong powering the most expensive part of the build with some cheap converter, right? To charge this battery, I used this constant current constant voltage charger board along with a laptop power adapter. This is required because charging lithium-ion batteries needs to be done in specific phases of constant current and constant voltage. Now that this was done, it was time for all the brains of RVAC. One of the most important things that made this whole project possible is ROS, which stands for Robot Operating System. ROS is a framework with all the tools and packages needed for this project like navigation, SLAM and many others. Besides that, it's easy to learn and has a large community useful for troubleshooting. The way it works is, ROS packages contain nodes, which are pieces of code that do specific things. Several nodes can communicate with each other through certain topics by sending messages, so they can work together. ROS core is what addresses and connects these nodes together and makes it possible to control the whole system remotely by connecting to it. So I installed Ubuntu 20.04 on the Raspberry Pi using the RPI manager. The version of Ubuntu is important, as ROS Noetic, the version of ROS which I used, is supported in Ubuntu 20.04 and not the other versions. In my case, I had to install the Ubuntu 20.04 server first and then convert it into desktop version by running this command to get the GUI for now, which makes it easier to set up and test everything. Then I followed the ROS installation guide and installed the desktop full version of ROS Noetic and set up the environment and workspace called Catkin Workspace by running the following lines of code. I also installed VNC server on the Raspberry Pi, following the process shown in this video so that I could access it from my laptop. After this, I wrote the code for the Arduino Mega to receive velocity information from the Raspberry Pi and calculate the necessary delay between each step for the motor drivers. The Arduino communicates with ROS running in the RPI through a node called ROS Serial Arduino. which I installed on the RPI and the Arduino IDE following this ROS tutorial. As for the step delay calculation, I first set an arbitrary microsecond delay which looked pretty fast. After that, I recorded it in 240 fps slow motion and played it back at 30 fps to calculate exactly the time it took to spin once and find the velocity at that step delay. Then to get any speed, we can take a ratio of the step delay corresponding to that speed. After that, I made a simple mount for the GPIO and the fan to cool the Raspberry Pi. Now to test the motors, I used a node called Teleop keyboard, which let me send translational and rotational velocity commands to the Arduino through ROS serial controlled by my laptop keyboard, which showed everything working fine. Then I spent a lot of time learning about and setting up everything in ROS to be able to do all that a vacuum cleaner needs to be able to do. The ROS navigation stack is a collection of nodes that lets RVac navigate autonomously. This requires input information like odometry and transform about the robot to be able to work. I made a publisher ROS node in Python that takes linear and angular velocity information from the command velocity topic and calculates the robot's position with respect to where it started, and publishes this data as odom and tf, which can be visualized by the ROS visualization tool called rviz. So after creating a launch file for the ROS serial, teleop, rviz and my odometry node, I can remotely control the robot and roughly see where the robot should be with respect to where it started. After that, I started working on the navigation stack, which will let RVac take goal positions and navigate there on its own. While everything seemed to be going fine, something pretty bad happened that ended up in me killing my Raspberry Pi. I just powered it on one day and the green light kept blinking periodically, but it just wouldn't boot. I tried everything I could to save it. I created a forum on the issue, which someone else also had, checked for LED flash signs, bootloader issues, and many others, but nothing worked. My best guess to what could have happened is that the cheap buck converter just stopped working and caused a voltage spike, which caused this. This was a huge setback because Raspberry Pis were not in stock anywhere at that time. So my only option was to wait for it to be back in stock somewhere so that I could order it. In this time, I designed and CNC'd some of the other parts of the body for later. To make the curved part of the body, I used this cool woodworking technique called curve bending, which works by cutting slits on the inner side of the curved surface and bending it bit by bit to get a smooth curve. My case wasn't perfect, but it got the job done. I stuck the rear curved piece onto the upper plate and made grooves for airflow. I also worked on making a bumper switch mechanism for the front curved piece, using these limit switches and 4 spring-loaded actuator style mechanisms that can detect if the front part of RVac bumps into anything missed by the LiDAR, but more on that in the next part. While I was trying to get navigation working on my laptop just using rviz, the Raspberry Pi 4 was finally back in stock and got delivered. And this time I bought this much better quality, fixed output voltage, 5 amp buck converter to power the Raspberry Pi through a USB cable. So after reinstalling Ubuntu Desktop 2004 using the command mentioned earlier, VNC and the whole ROS framework, I could finally start testing navigation. So here's how navigation works. The main node responsible for navigation is MoveBase. It contains 2 path planners called Global Planner and Local Planner, which come with their own maps called cost maps. Now these cost maps are basically grids with each pixel or cell assigned a cost to represent the likelihood of it being occupied. We get this occupancy information from a map being published by a ROS node called map server. Usually this map is created by the robot on the first run, which can be done using a LiDAR sensor and other nodes. But for now, as I don't have a sensor yet, I took some measurements and made a scaled version of the map along with its YAML file, which contains information such as image file path, resolution, and origin placement. With my custom ODOM and TF publisher node, the planners are aware of the position and pose of the robot at any time. With this, they can take a goal position request from the user and calculate an ideal path from start to end for the local planner to try and stay on by finally sending velocity commands to the Arduino to control the motors. This is just like the navigation stack setup found on the navigation page without the LiDAR nodes, which I'll add later. Simple enough, right? Well, this took a long time to get it working decently. It took experimenting with different types of local planners, and after settling on the DWA local planner, I had to play with its parameters like accelerations, maximum and minimum velocities, Vx and Vθ samples and sim period to see what they did and try to make it work properly within RViz. Eventually, after tuning these parameters and fixing an error in my code, it seemed to work. Before I tested the navigation, I made a few changes like this wire that connects the Arduino to the motor driver board so that it can turn off the drivers when the robot's not moving and the motors are idling to save power. After this was done, I created a launch file which launches all the nodes we need for navigation in one line. With this, RViz opens and we can see the local and global cost maps, along with where RVAC thinks it is. Once I place it roughly in the same spot, I can give it a goal position anywhere in the map using RViz and it will make its way there slowly. The green line is the initially planned global path that the local planner tries to stay on. The red line shows the local planner's projected current path. So I gave it a few more goal positions around the room. Now this does work, but after traveling and reaching its goal position a few times, the robot's actual position starts drifting away from where it thinks it is. This can cause it to think it is further away from an object than it really is and crash into it. This is why most of these vacuum cleaners come with either cameras facing up or LiDAR sensors to constantly scan the environment and account for this odometric drift. And since LiDAR sensors don't need external light sources and are easier to work with, I got this mini LiDAR sensor for this project. But that's about it for part 1. We'll deal with setting up the LiDAR and all the next steps in the next video, so that RVAC can generate its own maps and navigate completely autonomously. Thanks for watching. Catch you in the next one.